Okay, there we go. Now it is recording. Thank you very much. Okay, so looking at this advanced problem number 9 for the ideal gas law, we've got a sample of methane gas, and we burn it, and it makes carbon dioxide, and we want to calculate the volume of that carbon dioxide formed at a set pressure. To start with, we cannot allow Celsiuses to linger. Notice both of our temps are in Celsius. So what we need to do is we need to change those to Kelvin by just adding 273 to it. Okay, so I had 25 there plus 273 makes that 298 kelvins. And over here, we've got 398 kelvins since it's 125. Now, I also realize my calculator is far, far away from me, so let's grab a new one. All right. So I like to double check my math when I'm doing things. Yes, okay. So what we now have is we've got this methane that has that many liters, that many kelvins, and that many atmospheres, but it's becoming CO2. So we are going to need an equation for this, and that is our methane, which is CH4. It's combusted with excess oxygen, and this makes CO2 and H2O. As we balance it out, we need 2 waters to make our hydrogens equal, and that's going to give us a total of 4 oxygens in the product, so we need 4 oxygens in the reactants. But in the end, we're dealing with methane and carbon dioxide, so it's a 1-to-1 ratio. So 1 mole of CH4 is going to be equal to 1 mole of CO2. So that stoic step is just going to be a 1-to-1, but it's worth having it so that we at least know that it's there. So we are dealing with 2 things. We're dealing with our methane, and we're dealing with our carbon dioxide. So when we deal with the methane, we're going to pivnert that up because we've got almost everything we need. And what we want is we want to have moles left behind. So I'm going to quickly change my pivnert up by dividing both sides by RT. And what that's going to do is it's going to remove the RT from the right, put it to the left. So moles will be equal to pressure times volume over R times temperature. Now, the pressure is listed in the problem. As you can see there, it says that the pressure is 1.15 atm. So there's our pressure. So we're at 1.15. Now I'm not going to worry about units right now because if I have atm, Kelvin, and liters, then I'm going to get moles because of my R. Because remember, if we stick to liters, Kelvin, moles, and atm, we'll get liters, kelvins, moles, or atm. So I'm not going to worry about my units then, because as long as I stick to what I've got, I should be fine. Okay, and then I've got my V, my volume over here of 8.5. I'm going to have all of this is going to be over my R, which is 0.0821, and my temperature, which I calculated earlier, as 298. So this here is going to give us our moles of methane. So 1.15 times 8.5 divided by my R and divided by my temperature means I'm going to wind up with, let's colorize this in a way that stands out. Yeah, we'll do that. I'm going to wind up with 0.39954 basically. And this is moles of CH4. So there's my moles of CH4. Now what I can do is I can use this to get to my CO2 so that eventually I can get to my volume. So I'm going to need to do a little mole equation, a little bit of stoich, just to figure out how many moles of the carbon dioxide I have. So I'm just going to take my moles of methane and I'm going to convert it to moles of CO2. Now we know it's a 1-to-1 ratio, so the moles of carbon dioxide is going to be the same as the moles of methane, but I'm just going to go through the motions here so that it's all set and done. So here we now have the fact that we have 0.39954 moles of CO2. Now, so this here is my new N, because I'm going to want volume of CO2, but it's not at STP. So I'm going to need to do a second pivnert over here. But what I need here is I need my volume, because it's asking for volume. So that's not bad at all. I just do a quick little thing here of, okay, if I want volume alone, I just have to divide by pressure. That's going to remove pressure from this side, and I now have V equals nRT over P. My N is right there. I had just calculated that, so there is my first number there. That is going to be times R, so I've got my N times R. Remember, R is just our gas constant, times our temperature, and in this case we're using the temperature of CO2. Notice I kind of divided my screen into methane on one side, CO2 on the other. It's a useful trick doing things like that. So this, I've got my 398 kelvins are going to be there. But again, I don't worry about units, because as long as I stay in the units that I normally use, I'll be fine. And I'm going to divide that by pressure, and the pressure is listed right up here, which I'm going to use a different color for, 1.05. Okay, so that gives me my work here. All my math is all set up, so I'm just going to start punching this into my calculator. It's very critical when you do a double pivnert question that you divide your worksheet or your workspace, so that way you're not confusing one thing for another. I look back at my problem, I notice everything has 3 significant digits, so I'm going to take my answer and set that to 3 significant digits, and your final answer for this should be 12.4 liters of CO2. Does that answer your questions and help you out?
Yeah, it does. Thank you.
No problem. So that was a double pivnert question with some stoich in the middle. It's actually a bit harder than number 10 is, because 10 gives you the equation, but the difference is number 10, you're going to not have a 1-to-1 ratio. So your stoich step is not just going to change your units, it's going to change the numbers slightly too, but it shouldn't be too bad. And number 11, just you have to make the equation before you do all your math.
Okay, thank you.
So just to give you a preview to that. Did you want to do either of those?
Do you mind if we go over number 10?
No, not at all. All right, so just let me change this around. Just clear that for now. Let's import number 10 into here. That's a lot of stuff, so let's see if we can make it so that it doesn't mess up everything. Yeah, no, it's going to mess up everything. One program is talking to another. Give me 1 second. Okay, well, I'm just going to move this far, far away and pretend that it never doesn't exist. Okay. Okay, so it's okay. That makes no sense whatsoever why that happened. I'm not going to argue that. I'm just going to remove it. Okay, third time's a charm. Okay. There's the problem. And then separately, I'll import the equation. Okay, so what we are doing with this one is we have got let me make you bigger. Bigger. Thank you. I want to be able to see this easily. Okay. So this is number 10 on the ideal gas worksheet. We want the molecules of CO2 produced from 15.0 liters of O2 at 1.10 atm at 278 Kelvin that's combusted with excess ethane. So the fact that's combusted with excess ethane means we don't need to worry about the ethane. We can focus on the oxygen. If you see here, we've got liters, atms, and kelvins for the oxygen. Let's just let's change that. All right, good. Now it's not going to hopefully do that. No, it is. Okay. So we've got liters, we've got atms, we've got Kelvin, so we can get moles very easily through Pivner. So that is exactly what I want to start with. As I'm going to be working here with O2, and I'm going to set up a quick little Pivner. All right, now what I want is I want the moles again. And this is very common that when we use Pivnert, we want the moles. So it's going to be divide both sides by RT, like we have done before. And that gets moles all by itself equals to PV over RT. So RP is listed right there at 1.1 ATMs. RV is listed at 1.5 at 15.0, and then we have got our R, which is 0.0821, and our temperature, which here is listed as 278 kelvins. All right, so this should be able to determine our moles of O2. As we do that, punched into our calculator, and we find that we have 0.7229, and that's moles of O2. But I don't want that. I want molecules of CO2. So what I'm going to do is I'm going to take that in order to get my CO2. I'm going to then take what I have now, my 0.7229 moles of O2, and I'm going to change that over to CO2 using stoichiometry. So moles of O2 on the bottom, moles of CO2 on the top. If I look at my problem, I've got 5 oxygens for every 2 carbon dioxides. Now, it then wants molecules of CO2. Well, that's okay. That's just a mole step. I take my moles of CO2 down, and I change that to molecules of CO2. And that's the whole 6.02 times 10 to the 23rd power per 1 mole. So take that number times 2, divide 5, times 6.0 times 10 caret 23 equals, and I get my answer. And my answer in this case is 1.74. I have 3 sig digs. Beautiful. Times 10 to the 23rd power molecules of CO2. All right, do you see how I did that?
Yeah, I do. It's not as complicated as I thought.
Like I said, the number 10 is, or number 9 is much harder than number 10. Number 11 is a lot like what I just did, except you have to make the equation and deal with Celsius.
Okay. I can always just try that one on my own because I understand how you did these. I have a question though about changing to Celsius.
Go for it.
Is that just all you have to do is just take the degrees in Celsius and add 273 to it to get Kelvin?
Yep.
Okay.
And it should be on the back of your periodic table.
Oh, okay. I didn't know that.
No problem. Any other questions, Ava?
I think I'm good. Thank you.
Okay. I'm going to stop the recording then. Thank you very much for letting me record that.
Yep, no problem.